Alright, in an ADC, analog to digital converter, if you use an 8-bit digital signal to represent voltage range from 0 to 5, then how much is this so-called the Q, the quantization resolution? Alright, in order to calculate this, alright, you can just write it as that. Alright, this is your voltage, your voltage times 1 over 2, alright, to the power of your bit. In this case it's 8-bit, so I will just have 8-bit. If it's for example 4-bit, then I'll have 5 times 1 to the power of 4. Alright, if the voltage is 10, then I'll just write as 10 volt. So you see, 0 to 5 volt. So this is why we have used 5 volt over here. Alright, so far so good. So eventually you get 0.02 volt. Alright, so what does this mean and what are the quantization resolution? So in order to show you in a more graphically way, I'll have a time in the x and I'll have the voltage at that y. Alright, this thing is 5 volt. Alright, if you remember 2 to the power of 8 is what? Power of 8 is actually 256. Or normally we write as 256 minus 1, which is 255 values, because we start from 0 to 255. So if 0 is a value, alright, so 0 to 255, if you think about it, is actually 256. Okay, if you add, if it's 0, 1, 2, all the way to 255, then in total there are 256 numbers, because 0 itself is considered a number. Okay, I don't want to go into details on that, but at least you're going to know that we can represent our 5 voltage, alright, as 255 values. So this 0.02 volts is over here, alright, very very small, 0.02, 0.04, 0.06, all the way to your 5 volts. So over here at this side, you are dissecting your 5 volt in terms of 255 values. You see? So it's somewhat like a resolution, because you can re-represent your voltage as so many fine voltage, 0.02 volts. Okay? So in any of the, for example, if I have something like maybe I should zoom in. Let me see. I will zoom in this portion. Okay, I will zoom in this portion, and the rest are all going towards 5 volt lah. Okay, so in total I'll just repeat again, it's 255 values because it's 8-bit. Okay, so imagine I have a discrete signal coming in that is somewhat over here. It is about 0.03. Alright, then how should I represent this thing? Alright, because it's in between 0.02 and 0.04. You can either round up or you can round down, right? So in this case 0.03, I will round up to 0.04. Right, so over here at this side, I'll bring it up to this point. So this is somewhat like the quantization. So because your quantization is to round up to the nearest voltage that you can read. Alright, because your computer is a 8-bit. So you can read 0.02, you can read 0.04, you can read 0.06. Okay? So that's why if you have a 0.03, in order to read the 0.03, you can either read it as 0.02 or you can read it as 0.04. So in this case, we will read it as 0.04. Alright? And things like that, you see? The next wonder is that why do I have a 0.03 volt here? What is this about? If you think about it, if you have an analog signal, alright, this analog signal over here, this is a continuous domain in the real world. If you were to take different points, you take this point, you take this point all along, you take sample points, you have all these points all along. And all these points is just discrete points. Or we call this the discretization, correct? But however, these are all points that is, when you sample, is already here. But in order for your computer to read, your computer has to read in terms of how many bits the computer can read. Alright, it's talking about the resolution of the computer. Alright, so the resolution of the computer can only read 0.02, 0.04. So the intervals are 0.02 volts, because you add up 0.02, then 0.04, then 0.06, all the way to 5 volt. So the resolution is 0.02, is pretty much good already. Okay, and then this point over here, this particular point for example, is your 0.03. This is because you take the points at your analog signal. Analog signal is somewhat 0.03, and over here this is somewhat like maybe 0.054. So 0.054, if you take a look in terms of the computer one, now this is the quantization system, 0.054 is about over here, 0.054. So you can either round up again or round down again. Alright, so this is the thing or the rationale behind quantization. Alright, hopefully this will give you a good understanding of your quantization. So over here you have all this thing over here. Alright, if you were to quantize it, you will round up or you will round down all the stuff. Alright, so you will plot it in terms of how the computer can read. Alright, so the quantization is more on the how the computer can read type of stuff. Okay, and for you to sink in more vividly or more strongly, alright, I'll do another example right now. Okay, so imagine I have a 5-volt analog over here. If I were to discretize it, meaning I take each of the points, alright, I'll have this form over here. Alright, so you have re-represented your analog in terms of a discretized signal. Alright, it's just by points. By points in the air are all, we call this the discretized signal. Okay, so I would see that these discretized signals, these are all the voltage that it is, that my sampler can take in. Alright, my sampler. So I'm sampling each of this point and I put it into here. Right, so this is called the sampler and this is the process of sampling. Okay, for example, if I have only a 2-bit computer, if only I have a 2-bit computer, so 5 volt times 1 over 2 to the power of 2, because 2-bit, right? If you remember our resolution calculation, we can calculate by this. So I'm actually calculating my resolution now. Alright, so at the end of the day, I would have what? So 2 to the power square is 4, right? So therefore 5 divided by 4 is actually 1.25 volt. Okay, so over here if I were to just draw another graph, okay, we have 1.25, 2.5, 3.75 and 5 volts. So my resolution is only 4 representation of a 5 volt system. As you can see, I can represent my 5 volt in terms of 4 of these values. Okay, so if you take a look, 2 volts over here, alright, which I have over here 2 volts. When the computer can only read either 1.25 or 2.5, then I can either round or round down. So in this case, if I were to round out, I will have 2.5 volt over here. But instead, it is actually 2 volt in fact, right? Because the computer cannot read. Next, this is 2.5 volt. Alright, so by right, the computer can read now, 2.5 volts. Alright, and the next point is 2.7 volt. So the nearest to 2.7 volt is actually 2.5 volts. So you see, I've round down again, 2.5 volt. And over here, this is 2.75. So same thing, I'll round out again, 2.5 volt. Alright, 3.5 is near to 3.75. So I have something like this, 3.75 volt. So I'm actually round out or round down based on the nearest thing I can have. So over here, this is the 4 volt. If I were to round down, it's 3.75 volt, right? You see? And then over here, this is 4.5 volt. If I were to round up, I will have 5 volt. So you see, from a certain analog signal, you discretize it, having said that you have certain curve still, alright, until when you quantization it or you quantize it, you see over here is a straight line, and after that it becomes like this. You see, this thing over here is totally slightly different from this. If you were to superimpose, if I were to put this curve onto this analog signal and compare, you will somewhat look like this. You see, something like that. Alright, so you think about it, it's not very accurate at all. Although it can represent the curve, but in a way it is not very good. So therefore you want a more refined resolution. If you have a 8-bit for example, then somewhat your curve will be something like this. Although it's not very clean, but at least it's somewhere near your analog signal, you see. So this is why the 8-bit is some sort of a good way to represent our signal. Or if you're 32-bit, 64-bit, then you are going to have a more fine representation of your things, alright, of your signal or of your whatever thing that you want to represent. Okay, so this is the quantization through understanding, alright, and you need to know that. Alright, so the difference between discrete and quantize, hopefully in this video, can give you a very good idea of what the hell are they and how are they different from your analog. Alright, so these are all the things that I find is pretty useful, so I will leave you to this.